Okay, hello everyone, and welcome to this webinar. It's evening, around 9 o'clock in the evening in Sweden, and I guess it's 9 o'clock in the morning in New Zealand. My name is Peter Molnar, and I'm here to talk a bit about some of the wood smoke studies we have conducted in Sweden and some studies on health effect as well. And then I will have a second part which talks a bit about how to actually burn wood in an efficient and non-smoky way. So if everything works now, I will try to share my screen. So hopefully you will see the screen now. Wood smoke studies in Sweden and the proper handling of your fireplace with a nice picture of Gothenburg. The outline of this presentation is in two parts. First is what I said earlier about what we have done in Sweden and the wood smoke situation in Sweden. And the second part is tips and techniques on how to reduce your own emissions from your stove, and also showing a bit about the burning cycle in a real life situation. So biomass burning is the third largest energy source in Sweden for household heating. We have a lot of district heating, meaning that we have warm water in pipes below ground, comes into our houses, and electricity as well, which are the more common energy sources. But among single-family homes, the biomass burning amounts for about 1/3 of the energy use. And in Sweden, with a population just scarcely below 10 million today, we have 230,000 wood boilers and about 1.5 million stoves in Sweden today, with varying amount of use from complementary recreational use to main heating source for homes. In Sweden, like in New Zealand, we have many smaller towns where wood burning is very common, and in these small towns there is a potential problem for the local air pollution, and then of course for the health situation. What should be known is that the air pollution in Sweden is not mainly a domestic situation. If we look at the map of Europe here, you can see the center of these circles where the red arrow shows. There's an X where Gothenburg is situated. These concentric rings represent how long time an air parcel has to move before it reaches Gothenburg if we have an average wind speed of 5 meters per second. That means that southern Scandinavia is covered within 24 hours. Northern part of Germany, Poland, the Baltic countries, and the Netherlands are within 48 hours. In 3 days, 72 hours, we cover everything about except the Mediterranean, more or less, and within 96 hours, and meaning that 4 full days. We also cover major part of the Mediterranean countries, Italy and the former Yugoslavian countries, meaning that the air pollution in Sweden is just partly local. So a bit about a few of the studies we have conducted in real life situation in small towns. In the small town, some 150 kilometers north of Gothenburg, with roughly 8,000 inhabitants, there have been several years of reported annoyance to the local EPA office due to domestic wood burning, and we were approached by the local municipality and the local EPA office to help them to investigate whether domestic wood burning was a problem and how common and how big the problem was. As you can see on the bigger orthophoto, the overhead picture, we had an area which is encircled in red with roughly 8 single family homes situated quite close together with small gardens. This area was the center of the complaints. And what we did was that we put up a PM 2.5 measuring station, fine particulate, measuring daily PM 2.5 levels for 5 full months, 151 days during the full winter season for a year. Among these 80 homes, most people had a neighbor or a next door neighbor that were using some sort of wood burning appliances on a regular basis. And 35% of the subjects actually had one. So a bit more than 1/3 had one that was they were using, and that meant that the vast majority had a neighbor or next door neighbor that were using one. What we did was, apart from measuring in the center of this area, we also had, if you see in the lower part of this picture, see if I could use the mouse here. Here you see a small yellow triangle. We had the reference station here in an area where we didn't have any domestic wood burning in the nearby area as a comparison. And as I said before, the air pollution situation in Sweden is not only local. So what we usually do when we do air pollution studies in Sweden is that we calculate the regional transport using air mass back trajectories, meaning that by looking backwards in time from a certain day, we could follow the air, how it would have moved for the last 3 or 4 days, like in this picture here, and see where the air that we were measuring were originating from, and thus also gain some understanding on what type of air pollution could have been picked up while this air parcel has moved this way. And we usually have 4 or 5, in this case 4 different source regions. We have this Nordic, Scandinavian air masses, which are usually fairly clean. We have this one here, the continental, that goes over central parts of Europe, in this case Germany, Poland, and the Baltic countries here. We have a marine trajectory or air parcel, usually picking up mostly sea salt and some ship emissions. And then we have this one, this western, which we usually call a UK or similar, where we have both the Nordic Sea here, and we have the UK, and we could also have something from northern France. We could also have Ireland, Scotland, and so on. And these two to the right, the continental and the UK, usually have higher concentration of particles coming into us. So these are dirtier days when we have air from the Central Europe or from the UK North Sea, compared to the Nordic and marine air, which are more clean. And this becomes evident in the next slide here. This was the results from this 5 months daily measurements. And as you can see on the first row here, when we looked at all days in the wood burning area and the reference area, we don't see anything really different on average for 5 months. But if we look at the Nordic trajectories, the days with Nordic air, marine air, continental air, and air from the UK region, we can see that when we have the cleaner air masses from the Nordic and marine, we see a clear and definite difference between reference station and the wood burning station. And the average contribution in this case during this fairly mild and rainy and windy winter was around 1 micron. Pertaining that we have a bit more than 5.5 micron per cubic meter, it's almost a 20% share that is actually coming from the local biomass burning for domestic heating. We also did some bit more elaborate analysis by taking the filters we have sampled and not only weighing them, but we also did chemical analysis to investigate what type of elements we had. We did some source apportionment, and we compared the source apportionment between the wood burning station and the reference stations. And as you can see in this picture, for the long-range transported air pollution, usually sulfur containing and black smoke containing, the biomass burning, the sea salt factor, the soil, resuspended dust, and the traffic factor. The traffic factor is really small because this is a small community with a major highway going up towards Norway, some 3-4 kilometers away, but there's some forests area between, and we usually have the predominant wind direction coming from the ocean, passing our small town and then going towards the highway. So the highway influence is not that big, it's mostly local traffic. We can see that the wood burning and the reference stations contribution to traffic, soil, sea salt and long-range transport is almost identical, but we see a clear difference in the wood burning factor, giving us really strong evidence that we have a local wood burning source. So this is a confirmation that this simple trajectory method actually works fairly well, because 0.64 micrograms and between 0.7 and 1.1 micrograms is virtually the same. In another study, we made a bit more elaborate thing. We looked not only at the ambient air pollution in a small community, we looked at the personal exposure and the indoor air pollution levels as well. We went a bit further up north in the middle part of Sweden in a small town of called Hagfors. And as you can see on the right side, two scenic pictures, that this time we had a proper winter with sub-zero degrees for 1.5 months during the time that we conducted these measurements. Quite a lot of snow cover, and this is an area where the wood burning is very common, because as you can see in the pictures, there's a lot of forest nearby. Everyone has more or less free access to good quality wood. As you can see in the topmost pictures, you have birch trees that are very suitable for using as the heat source in wood stoves. In the middle picture, this cartoon graph, more or less, you can see that you have W's, which stands for houses in the study which were wood burners, and R's for houses that were non-wood burnings. They had electrical heating or heat pumps. That means that we, as a reference house or reference home, you were not allowed to have anything of combustion. So oil boilers, gas boilers, or gas heaters were not allowed for the reference, only non-burning material. If we look at the concentrations between the wood burning group and the reference group for PM2.5, we see that, and I should mention here that I've removed all the concentrations here, not to clutter the picture. The PM2.5 we measure in micrograms per cubic meter, and you can see there's a clear difference between the wood burners and the reference groups, with an increase of 6 micrograms per cubic meter on average for the wood burners in their personal exposure. Then we have a number of chemical elements and variables. We have black smoke, which is how black the filters are. And we see there's a difference in the smokiness on the filters. We can also see that for some of the elements, chlorine, potassium, calcium, copper, and zinc, we have a really strong difference. They are both red and bolded. And for lead as well, we see a difference as well, but not as strong, giving us good evidence that this is actually a wood source for the personal exposure, since these elements are attributed to wood and biomass. So that was for the personal exposure. If we look a bit more with black smoke, we compared, since we measure both indoors, outdoor, and personal exposure. On the left-hand side here, we have the correlation between the outdoor black smoke concentrations and the indoor concentrations. And as you can see in the left side picture, that the outdoor concentration was between roughly 0.5 and it's in a strange unit of 10 to the minus 5 per meter, up to a bit less than 1.5. So it's sort of within 3 times. But if you look at the indoor concentration, we go from almost 0 to 3. And the black dots represent the wood burning homes, and the circles, unfilled circles, represent the reference group. And you can also see that the reference group is tightly packed down here. No more any bigger difference between the indoor and outdoor in spread between the high and low concentrations. But for the wood burners, we see a large range, with a cluster up here for high levels of black smoke, and some which are actually as clean as the reference group. To the right side, we have the indoor concentration on the x-axis now, and the personal exposure for black smoke on the y-axis. And we see a similar thing. We see that all the reference homes are clustered in the low end quadrant of the graph, while the personal exposure is going along the one-to-one line up. And we see there's a good correlation, I would say very good correlation, between the indoor concentration and the personal concentration for the wood burners. And you might want to ask yourself, why do we have these clusters of wood burners down here, both for indoor compared to outdoor and indoor personal? Well, these are real homes. Some people have really good wood burning appliances that they use really well. Some of them also have boilers that are not situated in their living room or kitchen area or similar rooms, but maybe in a garage, which are sort of semi-separated from the home. So that means that when you replenish your boiler, you're not in your living space, but you're in this sort of semi-space, which is wall-to-wall garage area with or a shed thing, meaning that the indoor concentration for those who have those types of boilers will not be higher than the reference group. So from these two studies, we looked at the reported annoyance as well. And for the first study, where we only did outdoor, was this town of Tanum, which is this part here. And in Hagfors, apart from this wood burning area, we also had as a reference for the annoyance a district heating area in the other side of the town, some 3.5 kilometers away, so they should not be affected by the local wood burning. And when we looked at different types of reported annoyance. This was a fairly big survey with several questions, but I'm just taking the ones that has to do with air pollution, is that we could see that the annoyance for wood smoke is much higher in the areas where we have a lot of domestic wood smoke for residential heating compared to the area where you have district heating. While you can see that vehicle exhaust or problems airing the house due to smell or soot, the difference are not that big. And we also can compare this to the National Environmental Health Survey and see that on a regional scale, regions with a higher frequency of domestic wood burning on a full population level have a reported annoyance of 6 to 8%, while regions with lower frequency only have a 2 to 4%. So the annoyance is a real thing as well that we need to know about and actually see as a good sign that we have some problems. So how unhealthy are these wood smoke particles and gases? Well, we investigated that one as well, of course. We have conducted a few wood smoke chamber experiments together with colleagues at the technical research facility, and they have some really nice facilities. So we actually made this 45 square meter chamber, which you can see a picture of here, a schematic picture of, where we have a lot of control units here. We have a cast iron stove. You will see an actual picture of that one. We have the chimney coming up here. And then we take part of this chimney smoke, take it in here. And from the left side, you see that we have a filter system here. So we have clean air here, and we mix it, the wood smoke from the right with the clean air, to get sort of fairly stable concentration in here. We also have a lot of measurement equipment in here to be able to both control the indoor environment here and also to collect a lot of different filter samples for many various analyses. This is how it looks. To the right here you see the cast iron stove with the chimney coming up here, and here you see some of the participants in the study. People were staying 4 hours in this chamber with low activity, mainly reading, but as you can see in this picture, we also had some very light exercise to simulate moving, walking around and so on. So we shouldn't be fully sedated in a way that we just sitting on a chair for 4 hours half sleeping. And to the right side you can see some of the sampling equipment with several cyclones for different things. You have these Perkin-Elmer tubes and so on, which we used to collect various air pollution data. When it comes to the exposure, the concentration we had in the chamber for these 4 hours were around 250 micrograms per cubic meter on average, ranging from 240 to 280. The average 250 sounds really high, right? But 4 hours, if we take that and compare it to a 24-hour mean, this means that 250 micrograms per cubic meter for 4 hours are roughly equivalent with 50 micrograms per cubic meter as a full day mean. And that is actually the PM10 air quality standard for the New Zealand. You can also see that the PM1 mass, the really small particles, the ones that are less than 1 micrometer in size, they are the dominant mass. Over 99% of all the particles are less than 1 micron. If we count the number, we see that we are between 100,000 and 200,000 particles per cubic centimeters. And the ones that are below 0.1 micrometer, less than 100 nanometers, are usually more than half of these. You can also see that we have slightly higher NO2 levels. We have elevated levels of benzene, formaldehyde, and benzo-A pyrene. And looking at the exposure as the number concentration size distributed, you can see here that most of the particles are really small. You can also see that we actually not only did this wood smoke exposure, we also have control experiments with clean air. And the clean air were between 10 and 12 micrograms per cubic meter, which is what you can expect in a fairly clean environment. And we used this clean versus the exposure to look at some difference in inflammation markers and other markers. Here's an example of an acute phase reactant, almuoid A, which is a quick indicator of systemic inflammation. And if I tell you a bit about this picture, because it's a bit tricky. The gray diamonds are the concentration in the clean air. And at baseline, this point here is the concentration in serum in blood just prior to entering the chamber. So we have a blood sample just prior entering the chamber. Then we are exposed for clean air or wood smoke for 4 hours, and at time 0 is when we exit the chamber. So what we can see here is directly when we exit after 4 hours of exposure, we have an increased level. Then 3 hours after the exposure, it has continued to increase, so we have an even larger difference. And also after 20 hours, that means next day morning at the same time as when we entered. So this is actually 24 hours after entering, but 20 hours after the exposure was finished. We see it's still increased and statistically significantly higher all the time. Another example is the forced exhaled NO. And this is from our second smoke chamber study, where we not only used filtered air and wood smoke air, we tried to divide the wood smoke exposure between a startup wood smoke, which means the first 15 minutes after replenishing the stove, where we have a strong open flame. And then we also had a session where we just fed in to our exposure chamber the burnout wood smoke when we have the glow phase. So when the open fire in the stove has gone down to a glowing area more. And we can see that for Pheno 270, which it means that it's 270 milliliters per second exhaled, which is a stronger one, where we could get the lower airways, the alveolar region. We can see that the burnout wood smoke, which are the white triangles, are significantly higher than, of course, the clean air, but they are also higher than the startup wood, where we have the open flame. The same is for the Pheno 50, which is sort of the standard way, where you look at the larger airways in the bronchial tree. where you can see that the burnout wood smoke is giving a stronger human response than for the startup flame, meaning that, as we interpret it at least, that this is more black carbon rich. So as you can see that having exposure to levels that are close to or equal to the New Zealand air quality standards, we see direct inflammation responses in the human body. This doesn't have to mean that you get sick directly, but a prolonged exposure in this time will, of course, affect you over time, and sensitive groups will have a higher risk of worsening their health effects or developing health effects due to wood smoke. So how do we try to mediate this? Over to the second part, tips and techniques and how to reduce your own emission from your stove. In this section I will try to talk a bit both about different types of stoves, how they work and so on. I will also give some tips about how to actually use the stoves and also about handling on the wood. And as you can see here, this is actually my own wood storage. I have 3 of these sections, 2.5 cubic meter each, which I store for 3 or 4 years. And then I have a smaller section which is roughly 3 cubic meter, which I have just by my house, so I could just pop out and replenish my indoor log compartment to heat it for the last 2-3 days. And to the right you can actually see my own wood stove. And the principal function of a wood stove is that you have the airflows that comes both from the top and from the bottom, and you have the primary through the grate from underneath here in the right side. You have the primary airflow coming in to avoid smoking the front door, and you also have a secondary air purge air system coming here, which is preheated from the heat coming from the furnace area here. And we don't want to have cold air, because cold air will reduce the temperature in this furnace area. So we want to have as much warm air as possible. So having this top air coming in here as an air supply for the combustion will mean that we will have a better combustion situation. But of course there are a lot of different types of stoves. Here are a few examples, just pictures of them. If we start at the right side, we have this cast iron one, which is fairly common, especially in Norway, where almost everyone has one of these. You have this one, which looks really pretty, elaborate with big glass areas and so on. And you see this one in the middle, which is my favorite. This one is soapstone coated, and these one are probably one of the best one if you don't want to have a full boiler, because soapstone is a really good heat storage, and that means that when the fire burns down and you close the air intake and you stop the fire, the stone here is heated to something between 80 and 100 degrees, and it will continue for 8 to 12 hours to emit heat in your home, meaning that if you burn wood and you have a good fire for 3 or 4 hours, you will reach heat temperature in this soapstone that will keep warm for half a day. So you could start your wood burning cycle in the morning, and then after a couple of hours, when you go to work, for instance, you just turn it down, shut it down, and the heat from the soapstone will continue to warm your home until you come home. And then in the evening when you come home, you could start it up again and reheat it, and without having any smoldering fire during night, which is not an optimum way to use your stove. You still have the heat warming your home for the whole night. So to have a good combustion and high energy output, this is good both for the heating part, but also that it will lower the emission of the air pollutants. So what happens is when you start your fire, the wood is dried, and this requires heat to remove the excess moisture in the wood. After a while, the wood is decomposed and it starts forming gases, and then you will have this big flame. And most of the gases are burned in this temperature between 300 and 900 degrees Celsius. And then when you come to the high temperature phase is when you're reaching close to 1000 degrees. And then when you have the charcoal has been produced, and this is when most heat is released. So you want to be here as much as possible of your heating cycle. And to be there, you need to have dry wood. If you get wood from any type of source, cutting it yourself if you have a forest yourself, or woods in your garden, or if you buy it in stockpile or from some farmer or whatever, you need to dry the wood. You need to have the wood cut and stored in a proper way for at least 1 year, preferably close to 2 years. And if you keep it like in this left picture, stored openly like this, you will not reduce the moisture content below 50% if you're not in a really, really dry area. But if you just have a simple roof like this, you will reduce it down to 20%. It's also, as you can see on this right side picture, that having it open on the side means that the wind will help dry the wood. And having a moisture content of 16 to 20% are usually what's deemed to be sort of the optimum. And now I will try to see if I could stop this screen sharing and show myself again. Hopefully you will see me now, and I will show you just a couple of quick things, because I brought some wood logs here. To check if your wood is dry, you could use a wood moisture meter, which costs, I don't know, maybe 100 New Zealand dollar or a bit more. But you can also do a very simple test. If you get this sound, it means that the wood is dry. It's 20% or lower. This was wood that I have kept in storage for roughly 2 years. This is wood that I cut and stored this summer. This one has not reached sufficient dryness yet, but it will by the next winter. And you can hear that it's not this clunk sound, it's sort of a much more deeper sound. And while I'm still in picture here, I want to show one of the other things that's really good when you want to ignite your stove using one of these things. This is a small wax or paraffin ignition agent. This one burns for roughly 10 minutes. So when you put that one in, when you have stocked your stove, it doesn't you doesn't need to check and open the door to your stove in order to check if it's still burning, as is sort of common to use or to do when using newspaper to light it, because newspaper sometimes doesn't really make the fires catch up or correctly. So these things are really useful. I don't know really how available they are in New Zealand, but I guess you could find them in general stores. The price per unit is, I don't know, 5 to 10 cents. So it's sort of not any cost. And now I should try to go back and share the screen again. And hopefully we're back now. So now that when we have dry wood and we have this ignition agent, how do we do it in the right way when we light the fire? Well, you should have some smaller pieces of wood, and depending on the size and dimensions of your wood stove, you should try to have the larger logs in the bottom. Try to create spaces between them, and you should try to place this ignition module with the smaller ones on top. You can see it here. You could see one of these small wax things here. It's also here in this one, and it's here in this one, and it's here in this one. That means that when the fire starts, it starts burning in this local area, and then you will have a draft because the warm air will go up through the chimney, and that means that semi-warm air will go through these unburned logs below, and it will start drying them out without reducing the temperature in the fire zone. So now we have started a good fire if we do it like this. So we need to replenish, and there are a few simple things to think about. Avoid overloading. If you buy a new stove, that usually recommendations, if you have an existing one, you could learn it fairly quickly what is sort of suitable. Avoid too long logs. You want the logs to be actually on the charcoal glowing area and not up in the air. You should avoid only one big log. It's better to have two smaller ones. So cut this one up in 2 or 3 pieces and put the same amount in, but in several pieces. You will have a larger surface area, meaning that more area that could start burning. Also avoid having too large spaces between the logs, because this will be one separate fire and this will be one separate fire. Quick and easy way to see if you're are using your stove correctly is just go outside and check the chimney. If your chimney is emitting something that looks like that on the left side, you're probably doing something wrong. It could be that you have really wet wood, you haven't reached a good enough temperature, or you have put in things that you shouldn't burn at all. So like painted pieces of wood, treated wood, masonite, cardboards, whatnot. If you burn correctly, you should have something which is white, or just that you can see a heat flimmer. White smoke doesn't mean that it's dirty, it's water vapor that is condensed. So if it's white, it's not harmful. So now I want to, in the last few minutes here, I would like to try to go through a burning cycle here. So what I did was that last winter I took some pictures when I started my own fire in my home, and I just quickly walked through. This is start up 5 to 10 seconds after I put this one in. This is the small block of wax that is the sort of ignition agent, and you can see that I have some smaller pieces of wood up top and the larger logs are down. After 1 minute you can see that the wood has started to catch fire. You can also see here that there are some trails of smoke here coming when some of these volatile gases are released together with some moisture that are still there. After 5 minutes we have started to get a good fire in the topmost part of this log pile. Oh, 2 minutes, sorry. After 5 minutes, now the full upper part is burning, and you can see that it's only the lower half that hasn't caught fire yet. So this is how it looks outdoors, and I know these pictures aren't really good, but I mean, with the light condition, when I did this, I couldn't get any better. You could maybe see a small hint of some darkness here. It's much more visible actually when you're not taking a photograph with your camera. But this is due to that we haven't reached a proper temperature yet. We're still warming up the furnace now. But continuing on, this is after 10 minutes. Now we have a full flaming fire, and the heat is somewhere between 600 and 700 degrees probably in here. And now we can't see anything coming out from the chimney. And after 30 minutes, the open flame is starting to go down, and we're in the charcoal mode. This is the soon-to-be glow phase when we're supposed to start thinking about replenishing the stove now. I should mention that I always use fully open air supply at all time, because I want to have good air supply in, because that means that I will have an efficient burning, and since I have a soapstone, I will heat up the stone, and I will create this heat storage that I could use later on. So always try to avoid smoldering fire with low air supply. So after 30 minutes, nothing visible coming out, and 43 minutes was when I replenished. You can see that I have a couple of big ones and one which are a bit smaller on top, to have roughly the amount that is suitable for my stove. A thing to think about is when you open the hatch to replenish, usually you have a lock mechanism. If you just sort of unlock it without opening and wait for 5 seconds before opening and putting in new logs, you will remove this under pressure that you have in the stove, and have the pressure in your room and in the stove to be the same, and that will let you to avoid having a burst of smoke coming in, because if you just open the hatch directly, you will have a puff of smoke coming into your living room. So what happens now? 1 minute after, you can see that since I have a really hot furnace, this we were up around 1000 degrees Celsius when I replenish, it catches fire directly. You could see here that I know these pictures aren't really good, but there's some sort of minor hint of bit of soot here. This is because it's trying to burn this cement while it has, but hasn't really reached the full temperature at all. And 5 minutes after replenishment, you're in full burning mode, 700-800 degrees now. and you have a really efficient combustion. So check the chimney and the smoke to see if you're burning correctly. Black smoke, not good. If it's like in this middle chimney here, the picture, if it's sort of yellowish and so on, you have probably a lot of tar. And that means that you should have dried your or let your wood logs age more to reduce the tar when you reduce the content, the moisture. If you want to know more, there are a few New Zealand websites that we were showed when we were visiting New Zealand this summer or winter. Environmental Canterbury have a nice one, and this one, warmer cheaper.cu.nz, has some short information videos showing how you should use your stove. There are 5 or 6 2-minute videos. Please check them out. Warmer, cheaper, it's just what you should look for. So by that, I will thank you for your attention, and I'm open for questions and comments with a few scenic pictures of Gothenburg, my hometown. So thank you very much.